Shall we start?
Yes, we can start.
Yeah, okay. So audio video is fine or any lagging is there?
Perfectly
So
fine.
yeah, there was an issue earlier, I think. Maybe it is because it's heavy raining here in Delhi. So maybe because of that. Yeah. So let's start the session with the other title of this session is that Bell state measurement. So basically, we are measuring the qubits in every time we measure in Z basis, or we call them as a computational basis. So can we measure
Sir,
the? Yes, please.
sorry for interrupting you. Your presentation slides are not visible.
So I have shared this thing, not visible. So let me just
Maybe
again share.
network
Yeah,
issue.
yeah. Just a second. Just a second. Entire screen. Yeah. Okay. So is my screen visible now?
Yes, yes. Now it is clear.
Yeah. So Microsoft Whiteboard I have opened. Is it visible to everyone?
Yes, yes, yes.
Perfect. Perfect. So in this part, we will be seeing the Bell basis measurement. And before going to that, first we recall that there are four different Bell bases. Okay, these are namely phi plus, phi minus, psi plus, psi minus, and there are just slight differences between them. 00 plus 11 is called phi plus, which we have used every time in our quantum teleportation and super dense coding. Just one change is there, sign change. So these four are possible Bell states, and there is every time in these two state, phi plus and phi minus, similar correlation is there. Both the qubits will be measured to 00 or 11. In this psi plus, you will be having opposite. If you measure one qubit as 0, then other qubit will be 1. Okay, and vice versa. So these four are our Bell states, and we can see that these four Bell states form orthogonal basis. Why? Because for orthogonality and basis, we can see that this phi plus, if we take its inner product with phi plus only, then we get 1. So, so inner product is 1 with the same state. And if you take inner product with other states, like if I take inner product with psi plus, then it is 0. So any other two different Bell states, if you take and you compute their inner product, then it will be always 0. So what it means is, maybe you can take with psi plus and psi minus. So this property means these four states are basically orthonormal basis. Orthonormal basis. This state forms orthonormal basis. Why? Their inner product with self is 1 and with others it is 0. So they forms an orthonormal basis, and using those this four state phi plus, phi minus and psi plus, psi minus, we can represent any two qubit state. Okay, so any two qubit state we can represent, but generally in computational basis or Z basis, how we denote a single two qubit state psi 2, we just write like this: alpha times 00 plus beta time 01 plus gamma time 10 plus delta time 11. So this is the way we write a general two qubit state in computational basis. This 00, 01, 10 and 11 are basically our computational basis. So this is in computational basis. Computational basis. Okay. So can we write these states in Bell basis? Can we write this thing in Bell basis? Yes, we can write. But how? Okay. So basically this 00, if we can write in terms of phi plus, phi minus, so we can write like this. So let's call them as a equation 1, 2, 3, 4. 1, 2, 3, and 4. So if I add these two equations 1 and 2, then this 1 will cancel out and it will be 2 times of 0 0. So by using equation 1 and 2, the 0 0 can be written like this. 0 0 will be what? It will be nothing but 1 by root 2 of phi plus state plus phi minus state. We can write like this. Okay. So, and similarly 0 1 also we can write. So if you want to have 0 1, then what we need to do is just need to add these two 3 and 4 equation. If we add, then this 1 0 1 0 will cancel out, so we will having 2 times of 0 1. So it will be nothing but 1 by square root of 2, and it will be psi plus plus psi minus. So same way we can just 1 minus 2 we can get the expression for 1 1, and similarly for 1 0 we just 3 minus 4 will give us expression for 1 0. So suppose we derive similarly for 1 0 and 1 1, okay, in terms of this Bell basis. So what we can do is, so just we replace this value in this 2 qubit computational basis state psi 2. So for 0 0 we will place this thing, for 1 0 1 we will place like this thing, phi plus psi minus. So this way if we place them, then what we will be having is this psi 2 will be nothing but it will look like this. Psi 2 will be nothing but it will look like this. So it will be having alpha plus delta, alpha plus delta by root 2, alpha plus delta by root 2, and it will be phi plus, and it will be like for phi minus it will be alpha minus delta by square root 2, it will be phi minus, and plus beta plus gamma by square root 2, it will be 0 1, and beta minus gamma by root 2 1 0. So what we did is we just write the side 2 state which was there in computational basis 0 0 0 1 1 0 and 1 1. We converted it into Bell basis. So now what we are seeing is we have written the state psi 2 in terms of Bell basis. So earlier we have told that this 4 states can be used, this phi plus phi minus psi plus psi minus can be used as a Bell basis, and we are able to write the 2 qubit general state in computational basis, and we converted it into Bell basis. Now what we are saying is, here it will be, what, psi plus, and it will be psi minus. So here what we are saying is that just we rewrite the terms and we are able to get the state in terms of Bell basis. Now what I'm saying is that this is the state in Bell basis. If you want to measure in the Bell basis, then I ask you, what is the probability that this state is in phi plus state? So probability of this state in psi plus. So what will be that? That will be nothing but mod square of the coefficient. So the coefficient is this. So it will be alpha plus beta by root 2 mod square. Okay. Similarly, for probability of getting phi minus, this mod square. So just we have already written in Bell basis, and we can get the state in and their probability according to the Bell basis. So what is the probability of getting psi minus? That will be beta minus gamma by square root 2 mod square. So we can have a state in Bell basis and we can measure it. But how we can measure in Bell basis using computational basis only. So before going to the Bell basis measurement exactly, can we do how we can measure in Z basis? So just you remember from single qubit state, if you remember a single state qubit state psi is there and you measure it in Z basis, or we call it as a computational basis. So this Z is axis plus Z is denoted by plus 1, and we have it as a 0 1 state, and this minus Z is nothing but 1 state, and we can write as minus 1. So what we say is that whenever we measure this in Z basis, if we get plus 1 or basically plus Z axis, then we say that it is plus Z means we have observed 0, minus Z means we have observed 1. Okay, or just we write. So this psi is nothing but alpha times 0 plus beta times 1. So when we measure it, the measurement operation is defined like this. So what we do is simply psi state is there and we take its inner product with 0 state. So you will get the probability of plus Z axis, we denote by plus 1. So basically nothing but its probability of getting 0. So that will be mod square of this thing. So what we do in measurement is simply we do the inner product with 0 and 1 state. So minus 1, or basically getting the state in 1 state. So we do inner product with 1 state. So what we do in Z basis is we just do the inner product with 0 and 1 basis states, and we do the mod square, we get the probabilities of getting 0 and 1, or we denote them as by plus Z axis and minus Z axis. This way we do the Z basis measurement. Okay, so can we implement X basis? So here we are applying Z. So same thing, can we do it for X basis? So just I want to, we will be coming to that, because just a second, it has been closed accidentally. Just let it load again. So what we have seen is that psi state was there, general single qubit state, and when we measure in Z basis, so what we do is simply we do the inner product with 0 and 1 state and do the mod square of that thing. So we get the probabilities of measuring the result 0 and 1 respectively. Can we do the X basis measurement? So yes, we can do it. So how we will do it? That means state psi is there again, and you want to perform the measurement in X basis now. So in case of X axis, there are plus X axis. So this is like this, plus X plus X, and it is minus X. So minus X is nothing but minus 1 we call it, and it is minus state, and it is nothing but plus 1 we call it, and it is basically the state plus, and the plus is nothing but 0 plus 1 by root 2. Minus is nothing but 0 minus 1 by root 2. So in X basis, if you measure, so maybe you can get plus X axis or minus X axis. So plus X axis we call them as a plus 1 result, and minus X axis if you measure, we call it as a minus 1. And those states are called minus X, minus and plus states, and their equivalent in Z basis is 0 minus 1 by root 2, 0 plus 1 by root 2. So here if you want to measure in X basis, then the operation will be like this. So in X basis, probability of measuring plus 1 is nothing but inner product of this state with psi. So plus 1 means plus x-axis, then you need to basis, this plus and minus are the basis states. So you need to do the inner product with plus x-axis and then do the mod square. Similarly, for probability of minus 1, you need to do the inner product with minus state. Okay, so what we are doing is, here in x basis, if you want to measure it, then you need to perform the inner product with plus and minus states. So can we do this thing using z gate or z basis? Yes, we can do it, because we want to do everything using z basis or computational basis. Okay, what we want to do is, we do not want to have any other basis measurement. Whatever measurement, if x or bell basis, whatever you want to do, we want to implement them using z computational basis only. So for that, what we can do is, so suppose this x basis measurement is being performed by psi plus and psi minus inner product, so we can do it with z gate also. So how we can do it with z gate, that we can see. So in place of just psi, if we apply a Hadamard gate on the qubit and then we perform the z measurement, computational basis measurement, so this thing is nothing but this complete thing, Hadamard, then z basis measurement in x basis. Okay, we will show how we can do it. So the state psi is there, and if you want to measure it into x basis, then just apply Hadamard gate on it and then measure it. So this is Hadamard gate. So what we did is, psi was there, you apply the Hadamard gate and you measure it in z basis, and this is nothing but your x basis measurement. Okay, so we can check it also. So see here that whether these two are equal or not. So what we did is, we apply Hadamard gate on this thing. So psi will be what? H psi will be what? So alpha times plus, because we are applying Hadamard on 0 state. So it was like this, Hadamard alpha times 0 plus beta times 1. So we are applying Hadamard gate on the psi state. So Hadamard on 0 is plus state and Hadamard on 1 is minus state. So now your psi has become psi dash, and on psi dash you are applying the z measurement. Okay, what you will be doing, so you get this psi dash and then you will be applying measurement on this. So it will be nothing but what it will look like. So just we can rewrite this thing, alpha times, so it will be nothing but 0 minus 0 plus 1 by root 2, and it will be what, beta times 0 minus 1 by root 2. So if we just rearrange them, it will look like beta by 2 times 0 plus alpha minus beta by 2 times 1. And now you measure this state in Bell basis, oh sorry, in Z basis. So what you will get, what you will have, so probability of plus 1 is mod alpha plus beta by 2 square. See here, here also do this thing, then this is nothing but, so when you do this thing with psi, so this plus is nothing but what, plus is 0 plus 1 by and here is you are having what, alpha times 0 plus beta times 1. So when you do the tensor product or the dot product, so it will be the same thing. On measure with this alpha plus whole square, and on measurement 1 it will be this thing. So what we are claiming here is that if you put this just header mart here, then it will be as good as x gate basis measurement or x basis measurement. So what we did here is we wanted to measure in this bell basis. Okay, so what we did is for this x thing, x basis measurement, we have written in terms of like this. So some state psi was there and we are applying x measurement on it. It can be implemented using psi and then just put an header mark and this. So this thing, x measurement on psi is as good as header mod and then z measurement. So it is nothing but x measurement only. So with z basis measurement, we can do x measurement also. Just simply we need to put header mod gate before it. So for 2-qubit bell basis states, you require some operator. So here what we put header mod for x to z. So x to z measurement, just we need to put a header mod. So z can be converted to x and x can be converted to z with a header mod operation. So we just want to find an operation for unitary or operation which needs to be performed. So what will be there? There will be 2 qubits, q1 and q2, and we want to measure them in. So just a second. So 2 qubits are there, q1 and q2. You want to measure them in bell basis, and these bases are nothing but bell. Sorry. So you want to measure them in bell basis. So this 2 qubit system is there, q1, q2. You want to measure them in bell basis. So what you need to do is you need to perform some operation here and then measure in z basis. So here the operation for z to x was header mod gate. So here for this you need to apply some unitary u so that the measurement in unitary plus measurement in z is as good as bell basis. So it has been found that q1 q2 is there, 2 qubits are there. You just simply apply the control node gate from this qubit q1 to q2 and then apply header mod gate and then you perform z measurement. So it is as good as bell measurement, bell basis measurement. So what we are trying to say here is that if you want to measure a state in bell basis, so suppose you have your state looking like this. Your state in bell basis is looking like this: alpha plus delta by square root 2 phi plus phi minus psi plus psi minus. This can be a 2 qubit state in bell basis. But suppose you do not have bell basis measurement system, then you can implement the bell basis measurement using z gate only or z basis only. Just you need to apply these two gates, control node from q1 to q2 and then Hadamard gate. So these two gates, if you put before the Z measurement, then this thing will be nothing but bell basis measurement. Bell basis measurement. So just to keep this thing in mind that we can have, so we can rewrite any 2 qubit system from computational to this thing. So this thing is bidirectional. So any 2 qubit generalized 2 qubit system in computational basis can be written into bell basis, and vice versa. And if you want to perform or measure the state in bell basis, then you can do it by applying this two operation, control node from first qubit to second qubit and the Hadamard, and then you do the Z measurement. Then it is equivalent to bell basis measurement. And the bell basis measurements outcome will be what? There can be four outcomes possible there. So what are those possible there? So see here, the sorry, again it is closed. Just a second. Why? So it is crashing accidentally. So you remember from this Z basis, you will be having what output? You will be measuring either 0, 0, 0, 1, 1, 0 or 1, 1 on these two qubits, first and second. So based on this output measurement in classical bits, we can tell what is your bell basis was there or bell state was there. So that will be nothing but 5 plus. If you measure this thing, it will be 5 plus. It will be 5 minus, psi plus, psi minus. So what we are saying is that we want to perform the bell measurement, bell basis measurement, but we are doing this two gate operation and when measuring in Z basis. And on Z basis measurement, we will get this thing. So how we will know that this 0, 0 means 0, 0 means our bell basis measurement is 5 plus. So basically, if you see here, you wanted to see whether it is 5 plus, 5 minus, or 5 psi plus or psi minus. So on measurement outcomes like 0, 0, 1, 0 or 0, 1, 1, 1, we can see that these four states are there. So suppose if we measure these two bits as 0, 0, then we know that we have measured 5 plus. Likewise, other also. Sorry. So this thing you might have seen in quantum teleportation. You might have seen it in superdense coding also. That is widely used in those protocols and entanglement based swapping also. So the bell basis measurement is very important measurement and it is used in, see here, this thing was in quantum teleportation. What it was nothing but bell basis measurement. Okay, and the measurement outcomes were depending upon the values. We know that which bell state was measured. If you see here in the superdense coding protocol, see here again at the decoding of this bits, Bob is doing the bell basis measurement. So see wherever this measurement nothing is written, it is basically Z basis only. So here what we are doing is by applying control node and Hadamard, we were basically trying to find which bell state it was. So outcome will be 0, 1, 1, 0, 1, 1, and correspondingly we can have the bell basis or bell state. Okay, so this is for bell basis measurement which we have seen. So just I want to recap for everyone what we wanted to do and what we have done is we know that we have four different bell states, okay, like this, and these four basis states are basically orthonormal basis. Why? Because they have their inner product with self is 1 and other with others is 0, so they forms orthonormal basis. And any two qubit general state in computational basis can be written in bell basis like this. This is basically in bell basis, and we wanted to measure the state psi2 in bell basis. So that we have achieved by applying the C naught and Hadamard operation on the two qubits and then do the measurement in Z basis, and we are claiming that this is nothing but bell basis measurement, and the measurement outcomes like 0, 0 if we get, then we know that its state was 5 plus. The state 5 plus has been measured and it is being used for variety of applications in quantum teleportation, and super dense coding. So let's quickly take the questions if there are any question. Yes,
There,
yes.
there is one question.
Yeah, yeah.
Does Z measurement mean putting Z gate and then measuring it?
Correct, correct. So Z basis measurement is exactly the same. Basically, not putting Z gate. No, 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 no. Just understand like this. It is not like that. See here, if you remember from block sphere, if you remember, then it is your plus Z axis and it is your minus Z. And here we say that it is basically zero state, and here it is one state. So what we are trying to do is, suppose your state is somewhere here, with some theta. So it is closer to plus Z and it is further far away from 1 or minus Z state. So what we see in the measurement is, we do the inner product and we basically projecting this state vector on plus Z and minus Z axis. So we do the inner product and mod square, so we get the probabilities. So basically the Z basis measurement is that we are projecting the vector denoted by the state on plus Z and minus Z axis. Okay, and whatever the number we get, that is nothing but so we write like this: psi mod psi, just a second, let me write it again. So what we do is psi 0 mod square probability. So what we do is, so general, this is, suppose it is psi state. Okay, so what we do is, we do the inner product with zero state. So zero state is nothing but this kind of vector 1 0, and psi can be written like this: alpha and beta. So what we do is, we take the inner product of state psi and 0 and we get some number, and we do the mod square. That will be nothing but the probability of getting plus Z axis, or basically 0 state on measurement. Same way if we do with 1, then that will be probability of getting 1 state or minus Z on measurement. So the plus minus, when we mention this plus minus, basically means plus Z axis or minus Z axis. For X axis also the same way. So basically it is just the projection of that vector on the Z axis, plus Z or minus Z. So we are not applying Z gate. Z gate, if you remember, Z gate, what it does is, when it is applied on 0 state, it is remains same. When Z is applied on 1 state, it will be minus 1. So this Z gate is a operation for changing the state of qubit, or for computational purpose it is used. This measurement operation is just to measure the state, whether it is in 0 or 1, and their probability we want to know. So measurement in Z basis is to know that whether how much chances we will get 0 and 1. Here the gate Z gate on the states 1 changes the phase. Okay, so this is this thing. And if you want to understand with this block sphere representation, then the Z gate is nothing but rotation around Z axis by 180 degree. So the geometrical meaning is like this: rotation around Z axis by 180 degree. Any other questions here is there?
There is follow-up question. What is the limit of classical bits that can be used in SD coding?
Yes, only 2 bits we can send with single qubit. So if you want to send more qubits, then just for additional 2 qubits you will require additional 2 bits of classical bits. We require additional 1 quantum bit. So with one setup we can send 2 bit of classical information using single qubit. Any other question is there?
Yes. Can you please briefly show how measurement 1-1 corresponds to size state?
Measurement.
How
Okay.
measurement 1-1 corresponds to size state?
So context I am not knowing which part you were talking about. Super dense coding. In super dense coding, if you are talking, then we are just encoding one and one here. So for that, we will be applying Z and X gate on the qubit one. When we send this qubit after application of these two gates on Bob, Bob will apply these two operation for decoding the information, and on measurement it will get 1 1. So 1 1 is there, so you will get 1 1 state. So basically you get minus 1 and minus plus 1 state here. So in qubit state is like this. Just a second. So qubit state will be like
So the
this.
participant has clarified he's talking about the Bell state measurement in the recent topic, not super dense coding.
Yeah. So just let me see the question in detail regarding the Bell state measure. Can this be used for future quantum internet? Yes. So Himani has asked that can this be used for quantum internet? Yes. So super dense coding or what you are talking about? How decoherence or noise will be taken care? Can you just write in context like Koshal? Himani Koshal has written something. Himani Koshal, if Himani can clarify what she was talking about. Okay. So okay, so I can take the question by Lalit. She told that he told that. Just a second. No, no. For yeah. So Hemani, you have clarified. So you want to understand that whether this will be used for quantum internet or not. So yes, obviously this entanglement phenomena is very important, and there is a phenomena called entanglement swapping. That is an important phenomena which can be used for quantum internet. And maybe if time permits, I can cover this thing in 5 minutes or 10 minutes in the talk, coming talk. So these are very important phenomena. Super dense coding is just to send 2 bit of information using single qubit. So it is just to have the more bits you want to send in a single qubit. So super dense coding does not have application in quantum internet. But quantum internet has basically this entanglement phenomena which is used for transmitting the state from one state to other. So this entanglement phenomena on fiber optics can be survive till 100 kilometers or so. So in case of quantum internet, if you want to do a communication with larger distances, then entanglement swapping can be useful for quantum internet. Not only quantum internet, for quantum key distribution at larger distances it can be used, for quantum internet obviously, and for quantum repeater also. So maybe I can take one slide I have kept for you guys. So just a second, just a second. So this thing is coming out. So entanglement swapping topic is not part of this thing, but I can take this thing. So I'm just taking 5 10 minutes to explain entanglement swapping because it has wide variety of applications in quantum internet, quantum key distribution, and quantum repeaters. So there are three major things are there in which it can be used. So how we can implement entanglement swapping? So what we are saying is, suppose there are three parties A, B, C, Alice, Bob, and Charlie. So this is Charlie. And now what we are saying is Charlie is having two qubits Q1 and Q2, and Q1 is entangled with Q0, Hello.
Yes, we lost you for a few
Yeah, actually
minutes.
there was a power cut at my side. So are you able
Okay.
to see this thing screen, my screen now?
No, you'll have to share it again, I think.
Okay, okay. So let me just reshare it again. Are you able to see my screen?
Yes, we are able to see the screen.
Perfect. So in entanglement swapping, what we wanted to do is, so suppose there are three parties, A, C, and B. So A is entangled with C is entangled with both A and B. Now this A and C are not entangled. At the end of this entanglement swapping, what we wanted to do is we wanted to entangle the state of A and B directly without physically bringing them together. So this thing is clear. What we want to do is there is an entangled pair between A and C and another pair between C and B. And at the end of this entanglement swapping, we wanted to entangle A and B. So this thing is being achieved by this quantum circuit. So what we are doing is at the first step, we are creating entanglement between Q0 and Q1 with this Hadamard and control node. Second pair we are creating with Hadamard and control node between Q2 and Q3. Is the screen visible? Because I am using my mobile's internet. Hello?
Yes, it's visible.
Visible and audible also? Drawing
Yeah,
and
audible also.
perfect. So what we did is we created two entangled pair Q0 Q1 and Q2 Q3. And C is a intermediate Charlie which is having Q1 and Q2 which are part of entangled pair 1 and 2 with A and B. So what we are doing is we are doing this thing that is what we call, if you remember, what is it? It is nothing Bell basis measurement. So Charlie is performing Bell basis measurement on her qubits Q1 and Q2. Okay. So Charlie has performed. So Charlie will measure some bits A and B. Okay, small a small b. Suppose it gets both of these bits as 1 1. Okay. So now what we are saying is that these two were initially A and C. A is entangled with C, B is entangled with C, and C Charlie was having these two qubits which were not entangled. So, but what Charlie is doing is performing Bell basis measurement on her qubits Q1 and Q2 by this operation control node and Hadamard and then measuring them. So we have just now seen that this is nothing but Bell basis measurement. After Bell basis measurement, suppose it has observed these two bits. So it will get classical bits A and B. Those are suppose 1 1. Then if you apply the control node gate from this B qubit to first qubit and control Z gate. So it is nothing but control Z. So whenever this is 1, the Z gate will be performed here. Whenever this is 1, X gate will be performed on the first qubit. First qubit Q0 is with Alice. So at the end of this process here, when we apply this plus and Z operation depending upon the value of A and B, Alice and Bob's qubit Q0 and Q3, they will be entangled. So now Q0 and Q3 are entangled and they will be having the state what? They will be having the 5 plus state 0 0 plus 1 1 by root 2. So see what we are trying to say here that initially this Q0 and Q1 were entangled, Q2 and Q3 were entangled. Then C performs Bell basis measurement on her qubits Q1 and Q2 like this, and she observe A and B values. Depending upon A and B values, so what Alice Charlie needs to do? So Charlie needs to tell this A and B to Alice that I have observed Q1, or basically Q1 as 1 and Q2 as 1. So depending upon these values, so suppose Charlie told this that I have observed 1 1, then Alice will apply plus and Z gate on her qubit. At this end of this, Alice and Bob's qubit will be in this kind of superposition or entanglement state 00 plus 1 1, although they physically did not interacted at all. See, so Charlie will do measurement. This, depending upon the value of AB, Alice will apply this plus and Z operation, and then finally their qubits angled. So is this thing clear? So any questions are there?
Yes, questions are there.
Yeah, just a second, let me take. Yes, so Himani is correct. So entanglement swapping is used to increase the entanglement distance. Yes, and see here, if this original entanglement was, suppose it is between this distance is suppose 100 km, we can perform entanglement. After that, suppose our entanglement destroys or deteriorate or not that much, then this way we can increase the distance of entanglement from 100 to 200. And likewise, if we do it in cascading or this nested way, then we can increase further. Okay, so this thing is used in QKD also. If you remember, in QKD what happens is that we have suppose on fiber from A to B, we can establish secure key at distance of suppose 150 kilometers. Okay, now we want to do a QKD at a larger distance, and we want to go to suppose D, that is again far away, dates 150. So what we can do is, in between, if we can have this kind of entanglement swapping phenomena, then with C we can create entanglement between A and C, and again with again more pairs of this entanglement swapping, we can create entanglement between A and D, and then we can increase the distance. So this entanglement swapping can be used as a quantum repeater as well. Okay, so suppose we are able to cover this distance, then if you want to go for larger distances, then entanglement swapping can be used as a component to increase the distances. And it is very much useful for trusted node also. So this B should be trusted node, because it should not be like someone can change or do something malicious thing on this thing, because QKD offer perfect security or secrecy. Then if this we are using entanglement swapping for this increasing the distances, then it will work as a trusted node, and it should have those entangled swapping concepts. And same thing, similar way, this entanglement swapping can be used for quantum internet as well. So okay, this thing is clear, I think. You can take a couple of more questions. Yeah, so Hemani, your question is answered. Yeah,
One more question was there. If you scroll up,
Lalit.
this one.
Yeah, so recycling my earlier question, you wrote down that Z final Z basis measurement in Z. Yeah, question, can you please briefly explain how the final Z measurement 1 1 corresponding to psi? Okay, so yeah, so the question was how we can suppose. Okay, just a second. So the question was that okay. So the question was how you are able to make sure that 1 1 is corresponding to psi minus. So the derivation which we have done for super dense coding and quantum teleportation, similar kind of derivation we can do step by step, and we can say that okay, at this final we are getting 1 1 only on measured basis measurement. So basically, step by step derivation if we do like we have done for super dense coding and other teleportation, the similar thing we can do for this kind of measurement as well. and on measurement we can prove that it is the same which we desired. And also, if you recall one thing that, yeah, derivation we do not have time, but one thing is there. If you remember, if you want to create a state like psi minus, then you use this kind of circuit. Hadamard control node, just a second, yeah, and then you have, that is nothing but 0 1 minus 1 0 by root 2. So you see here, this kind of Hadamard plus control node, and initialize these two qubits Q1 and Q2 with one state. So Q1 and Q2 are initialized with 1 1 to create this psi 1. If you perform the Bell basis measurement on this, so basically what we are doing is we are again applying. So just I'm taking this thing out. So at this point we have psi minus here. So what we are doing in Bell basis measurement, first we are applying control node operation and then Hadamard operation, and then we are performing what, Z measurement. So, and what we are calling it complete, we are calling it Bell measurement, and these are nothing but Z measurements. So see here, we started with 1 1 state, and then we created Hadamard side control node gate, we get psi minus state. Suppose if we are applying Bell measurement, so Bell measurement is nothing but control node, Hadamard, and then Z measurements. So if we perform this thing, then what we are saying is that we will be observing 1 1. That means we have psi minus. So see here, the state was like this, and on this state, if we apply control node and then Hadamard, then we will have 1 1. So derivation will take time, but you understand this thing. C naught is self inverse, so C naught will cancel out. H is self inverse, so H is also cancelled out. So what we will remain? We will remain with 1 1. We will remain with 1 1. So basically we will get 1 1. That it means our state was what? Psi minus. Otherwise, step by step derivation of this thing we can do with C naught and Hadamard gate. Any other question over there? Okay, so Lalit,
Yes,
your
there are few
question has been
questions.
answered. Yeah, any other question?
There are
Can we
few
use the,
questions.
I missed where it is. Need to go. I think I have answered most of the or every question. Yeah, yeah. Just a second. Which question is missed? Yeah, this question. Super dense coding doubles the capacity. Is there any other way to increase the capacity beyond that, like M array? Yeah. So with Bell state, 2 qubit Bell state, we cannot increase it beyond. Just using single qubit, we can send only 2 qubits of information. So with Bell state, the limitation is there. We cannot go like this. So yeah, I think most of are answered. Yeah. Any other question is remain answered, then they can write. Yes, there are. Yeah, no, there is no paper like this how to increase the efficiency of super dense coding, but simple idea is there. With one Bell pair, you are able to send 2 bit of information from a single qubit. So if you use 2 Bell pairs and 1 qubit you will be using for sending 2 bits. So with additional Bell pairs, we can send 2 bit of information. Okay. Or maybe from Alice point of view, if you see it, then with 1 qubit, 2 bits of information. With n qubits, 2n bits of classical information you can share. Shashwat, is it answering your question? Okay.
So that's the
Okay.
last
Thank you.
question.
Yeah. Which one?
I mean,
Yeah.
that's the last question which you have already addressed.
Yeah. Yeah.
All right. So we would like to thank Dr. Harish Rao for these 4 wonderful sessions. And I hope the participants have enjoyed these sessions because he has been very interactive where you can, the chat windows are also showing that people have actually enjoyed these sessions. And I would like to thank you for taking your valuable time for these 4 sessions, and also um, accepting our last minute request to change your schedules for the 2 sessions. Uh, and so basically, a big thanks to you.
Okay, thank you, participants, for patiently listening and understanding the things. And thank you, Professor Mitharwal, for inviting me for the course. Thank you.
So we'll be ending this session. Thank you very much. Thank you all.
Okay, thank you.